Okay, everyone, good morning. I'm Fausto Gallucci from OneCube, and it's my pleasure to invite you and to follow this webinar. This is the first of a series of webinars on chemical looping, and is co-organized by 3 projects, which are Bio-FlexCLC, COUPLED, and Bio-MeGaFuel. In all the 3 projects, there are aspects of chemical looping, whether it's gasification or reforming, fluidized bed or packed bed. So we thought that was a good idea to join forces and to give this webinar. Today we have 3 speakers from the 3 projects. We have Professor Vincenzo Spallina from COUPLED. Then we have Professor Tobias Mattison from Bio-FlexCLC, and Dr. Jochen Scroll from Bio-MeGaFuel and Bio-FlexCLC. The idea today is that we start with a very brief introduction of the projects, around 5 minutes per project, and then we will go more in detail in the scientific part of the projects, of course, related to chemical looping. And to start with, I would like to ask Jochen to start with the short presentation of Bio-FlexCLC. Jochen. We don't see in presentation mode. Yes, now it is, but you are muted.
Okay, I hope you can hear me now.
Yes, perfect. Yes. Please.
So welcome all to this brief presentation of Bio-FlexCLC, which stands for Flexible Chemical Looping Combustion for Combined Heat and Power Production from Biogenic Residues with Negative Emission. So this project is actually coordinated by RISE, by Amir Suleimani, but unfortunately he cannot participate today. So myself, I'm going to present instead of him. Yeah, just a brief overview of the idea of Bio-FlexCLC. So the idea is to have a flexible mode that can change between 2 concepts. The one, maybe I start with the right-hand side. This is a conventional CFB technology. CFB stands for Circulating Fluidized Bed Reactor. So this is a conventional system for producing heat and power. And on the left-hand side, you can see a chemical looping system. And this has a particular similarity that it's also working with CFB. So the reactor, which is used as a boiler in the conventional mode, can then be used as an air reactor in the chemical looping system. And then we add an additional reactor, the fuel reactor, which is needed to reduce a metal oxide and then transport oxygen to the air reactor. I won't go now into the details of the concept because I have only 5 minutes to present the project, so the details will follow later. So Tobias, he will talk a bit about this. Yeah, so the idea is to switch between these 2 operative modes, depending on whether, for example, it is advantages from an economic point of view to separate CO2, because chemical looping combustion is an inherent can inherently separate the CO2, so we can reach even negative emission when using biogenic fuels. And then if in operation modes and in time periods when CO2 storage or transport or whatever is at the moment not feasible, or from an economic point of view not positive, then we can switch to CFB. Okay, the advantages of the system is a strong compatibility with existing infrastructure, so we could even use existing CFB technology and then extend it to chemical looping. We can switch between CFB and CLC depending on market conditions. We have high efficiency and low cost if we want to capture the CO2 due to the features of the chemical looping system, which is a very low CO2 avoidance cost of around 20 euro per ton, and possibilities for negative emissions when using biogenic fuels. So since it is a fluidized bed technology, it's very flexible towards feedstock, so we can use biogenic residues and waste without a high cost for pre-treatment. It's flexible also towards load fluctuation, and it has a feature that it can potentially have a low corrosion with improved steam data and high electrical efficiency. Also, one advantage is that the emissions of SOx and NOx are relatively low. Now, what are we going to do within the projects? We want to further understand for chemical looping combustion of biogenic residues. So 4 different biogenic residues are tested in chemical looping operation in various plants. Then another objective is to reduce the emissions of harmful gases and particles. So we are developing a gas cleaning procedure to reduce SOx and NOx aromatics and also particle emissions, and also test the liquefaction of the CO2. Then to improve the conversion of fuel by adding packings in the fuel reactor and also in a post-combustion chamber. So we have different tests, pilot scale, and the aim is to reduce the fraction of unconverted fuel in the fuel reactor to get an oxygen demand below 10%, which means that 90% of the gases can be converted in the fuel reactor. Also to reach 99% conversion in the including the post oxidation chamber. Then we evaluate the flexibility by changing the thermal input into the system, and also develop strategies for optimized operation regarding the heat to power ratio. Various ratios will be investigated. We evaluate the economic and environmental performance of the process concept at 2 locations by adopting this Bio-FlexCLC in regions in low transition from fossil fuels. So this is techno-economic life cycle assessment here. Then to demonstrate the Bio-FlexCLC at megawatt scale with downstream treatment, here we operate a 1 megawatt Bio-Flex plant, both in a CLC and CFB mode, and the aim is to have at least 2 hours of operation and high capture of more than 95%. And finally, design a 100 megawatt commercial Bio-FlexCLC plant for CHP production. Some numbers. So the duration is 48 months. It started in June 2024, around 4 million of funding, and we have 10 consortium partners from 7 countries. So here on the map, we have RISE as the coordinator, Eichenic Engineering, which is an engineering company for CFB system. We have Götaverken Milieu, they are taking care of the gas treatment. Then we have the universities in Darmstadt, also Chalmers University, doing the testing and at pilot scale. Also CSIC from Spain doing testing. We have CERT from Greece doing CFD modeling, OneTube for exploitation, dissemination, communication. Fortum and Vecture, they are two utilities operating heat and power plants. So yeah, that was a brief summary of Bio-MeGaFuel, and then I pass.
Thank you very much for the nice introduction to the project. Of course, for the participants, if you have any question at any time, you can use the chat or the Q&A, and the presenters can answer, and we can answer also later. So don't be shy to ask even detailed questions. Good. Then I would like to ask Vincenzo Spallina, as coordinator of COUPLED, to give the short presentation of the project. Vincenzo, yes, we see the presentation.
Okay, good. Thank you. Thanks everyone. Thanks Fausto for the introduction. I'm going to present today the COUPLED project, which is stand for CO2 utilization process via looping technology demonstration. Just a second. Okay, yeah. So see if it moves. Yeah. So the project started in 1st of November. So it's really started a few 3 months ago. It's a project with 15 partners from all over Europe. So you can see partners from the UK, such as Johnson Matthey, University of Manchester, which is coordinating, partner from Netherlands, namely Zefira, Ilical Energy from UK, Finocas from Belgium. We have also partners in Italy, such as Insight, Wood, Snam, Contarina, Techfem, PNO, and IMI, and then partner from Greece, Etam, and partner from Turkey, which is Sokar, and from Spain, Technalia. So what is the idea beyond COUPLED? So the idea is to develop two different approach for syngas production, and the syngas production is then moving to the production of potential liquid fuel or methanol, or used for direct reduction of iron. So in the case of syngas production, we are looking at one option, which is chemical looping reforming, where we will use biogas and CO2. The second option is reverse water gas shift, where we will use green hydrogen and CO2. Now, in order to generate syngas, we need to also provide energy, and the energy is coming from the valorization of the waste gas. So as a possible option, we are looking here at flare gas from refinery, syngas generated in residual solid waste gasification, as well as also gas coming from steel plant, such as blast furnace gas or electric arc heat furnace gas. Now, when these gases are used in a chemical looping configuration, they go through oxidation. Therefore, you can generate flue gas, which have a higher concentration of CO2. The next step to combine make the process low carbon is to separate the CO2. This is happening through a membrane, from which we can then send to the atmosphere CO2 depleted flue gas, and the CO2 which has been recovered from this flue gas is recycled back and used within the syngas generation process. So we have an in situ CO2 reuse. So if you look at the full scale, you will have in the center, there is a chemical looping system, which is primarily looking at generating syngas from the system, and also carry out the reduction of the metal oxide by producing concentrated CO2. Then we have a membrane, and the membrane is used to remove CO2 from the reduction gases and send it back for the syngas generation. And then we have also the oxidation part to provide the heat. Finally, syngas can be generated in a Fischer-Tropsch technology, which is also part of the study. So we are planning to develop technology such as chemical looping in packed bed reactor, we aiming to develop a new technology, which is also membrane for CO2 purification, CO2 concentration in this case. In terms of value chain, we have different applications which envisage the use of green hydrogen, biogas, and refinery gases, but also use of CO2 and use of blast furnace gas, flare gases, and waste to energy. And on the product side, we are looking at production of pig iron, methanol, DME, and liquid fuel, or potentially in the case of green hydrogen, we could also look at methanation. You can see all the industrial partners which are involved in either technology production, technology providers or end user, but also we have engineering company which will look after the cost analysis and the EPC design, but also environmental, society, and commercial assessment support to boost the impact of the technology. If you want to look at the full process of the full value proposition, we have material and component development with different partners involved in their preparation, optimization, and delivery. We have process scale up, so we are aiming to go to TRL7 to demonstrate the different part of the process. And obviously, we have the industrial development, which is where we are trying to understand how costly and how feasible will be this technology. That's all from a couple project. I just want to highlight, I will do also later on, that this year there is the International Chemical Looping Conference, which will be from August to 4th of September in Manchester. And abstract submission, its deadline is the 27th of February. So hopefully all the community, which should be quite well represented in this webinar, will also join the conference later in September. Thank you.
Thank you very much, Vincenzo. Then I would like to ask again Jochen to do a short presentation of Bio-MeGaFuel.
Okay. I hope everyone can see the presentation. So welcome all also to the Bio-MeGaFuel presentation. Bio-MeGaFuel stands for biomethanol production via chemical looping gasification coupled with membrane reactors. Here's actually the same situation as for BioFlex. So Amir from RISE is actually the coordinator, and I'm presenting instead of him. What is the aim? It's to develop a novel, efficient, and scalable project to convert low-value biogenic residues and organic waste to biomethanol through chemical looping gasification coupled with membrane reactors. So here you can see a sketch of the scheme. On the left-hand side, we have a chemical looping gasification system. It looks quite similar as a chemical looping combustion system, just that we do not have aim for a full conversion of the fuel, but only for a partial oxidation of the fuel, so that we have a syngas as a product. And this syngas we have to clean, and then we can accommodate the H2 to CO ratio by adding some renewable hydrogen to get a perfect ratio for the membrane reactor methanol synthesis. So this ratio is around 2. And in the membrane reactor, we can separate the methanol from the other components like CO2 or H2O, which are recycled back to the gasifier as a fluidization gas. The focus here in this webinar will be on CLG. So the presentation I will show later is on the CLG project. But the membrane reactor is also important system in the project. The advantages is we are flexible towards feedstocks, utilizing various biogenic residues and waste, since it's a fluidized bed technology. We have a high conversion efficiency, higher than conventional gasification, and methanol synthesis lead to lower production cost and maximum biogenic conversion to Biomethanol, we are reducing the number of downstream units. So in conventional system, we first have a CO2 separation, and then afterwards methanol synthesis, and we have combined it into one unit. We produce biomethanol with near zero emissions. Somewhere else, yeah. And the process is less energy intensive and self-sufficient in terms of heat. So what is the methodology we are going to use? So we are developing this waste and residues gasification with oxygen carriers to maximize the conversion of the feedstock. So we will test 5 biogenic fuels. These are, or we are already testing it in a small scale. It's a microalgae, buckwheat, wastewood, olive pits, and spruce. Then we operate a 1 megawatt pilot plant in autothermal mode to gasify around 50 to 70 tons of residues. So we are aiming for TRL5 in this unit. The gasify, we aim for 80% gasifier coal-to-gas efficiency for a commercial unit. So usually in the pilot plant, we have a bit less due to higher heat losses. And we are aiming for 98% carbon conversion in the gasifier and less than 10% of reactive ash species released in the air reactor, because we assume that most of the ash species will be released in the fuel reactor. Developing membrane reactors for methanol, since they must demonstrate the membranes at TRL5 in standalone setup to produce biomethanol and significantly increase the yield of biomethanol from syngas by twofold, and separating unconverted products and biogenic CO2 to recycle back to the gasifier. Do process evaluation and sustainability analysis, design a full process chain, compare different configuration, estimate CapEx and OpEx, estimate carbon footprint, and assess also social and economic impacts. Exploitation and value chain analysis. So we are looking into market production, end user uptake analysis, and value chains and business models. Some numbers here also, 48 months. It started in September 2024. Budget is a bit less than 4 million euros. And we have 9 partners from 5 countries. These are 3 research institutes, RISE from Sweden, CSIC from Spain, and IVL also from Sweden. We have 4 companies, Gidara Energy, this is a gasification technology partner, Perpetual Next, so they are into the biomass pre-treatments, OneCube for the methanol and also for dissemination, and Blue World Technologies. Then we have 2 universities, Technical University of Darmstadt and Eindhoven University. Yes, that was a brief overview, and then I think we can continue with the main contents of the projects.
Thank you very much, Vincenzo and Joachim, for the introduction to the projects. I want to remind to the participants, if you have any question, please put in the chat or Q&A, and we will answer. And now it's my pleasure to ask Professor Tobias Mattisson to give a presentation about Bio-FlexCLC, and this is especially about chemical looping combustion. Tobias.
Yes, thank you. Can you hear me?
Yes, we can.
That's good. Yeah, perfect. Thank you. So since I'm blind, I will have my colleague here, Nasreen, help me put this, try to put this presentation on board here. So.
That's perfect.
Okay, so it's on there now. So yes, so my name again is Tobias Madison, and I'm from Chalmers University of Technology. So today, my presentation here will, Joshan made a very nice presentation of the Bio-Flex project, the project which was started about 18 months ago. So in this project, we're kind of right now generating a lot of results in the different work packages, but perhaps no ongoing results. So I will kind of present a little bit about chemical looping, what we're doing at Chalmers, and how that ties into the Bio-Flex project. So I would just like to start that I've been in this area of chemical looping and carbon capture for a long time, and it's I think I have a screenshot here of a conference from back in the 90s about greenhouse gas issues. I think it was the first conference I went to around carbon capture, and even looking at the table of contents in this, it was very dire and very need for a very rapid decarbonization and deployment of CCS. Today, 20, 30 years later, I think we're emitting 60-70% more CO2. So in many ways, we have kind of in the community or in society perhaps failed. But I would like to say that there are many things that are positive and there are things going on. And I think that CCS and perhaps also CCU is really needed for rapid deployment. And we are hoping that this Bio-Flex and perhaps the other projects presented here will have that kind of effect. So anyway, chemical looping, since I'm the first detailed presentation, let me just do some background, since I guess this is a general webinar and it's public. So in principle, if you're going to do CCS and CCU, you would like to have, you can do this from a fuel conversion process, like a combustion. But the normal combustion processes and are usually result in the conventional way in gas streams which have about a lower concentration of CO2 than pure CO2, maybe 5 to 20%. And what you need in order to use it is often that you need to have it in very concentrated form. So a lot of the challenge with CCS through the years is to go from 5 to 20% to pure CO2. And everybody knows that this is nothing that is done for free often, because if you need gas separation, then you will have a thermodynamic work in order to obtain this. You can never go beyond this, as far as I know at least. But in chemical looping, what we have is a way to avoid gas separation. The way it works is that you have a fuel reactor. You have two reactors. You have a fuel reactor where the fuel is introduced and it reacts with a metal oxide oxygen carrier. Could be like iron oxide, copper oxide, ilmenite, things like this. And the fuel grabs the oxygen and produces CO2 and water in the fuel reactor. And after condensation, you should obtain a rather pure stream of CO2. The reduced metal oxides are transferred to an air reactor where they are oxidized back to full oxidized state. And here it's basically just grabbing the oxygen from the air. So what you have in the outlet is a depleted airstream with some oxygen, but mostly nitrogen. So this is the cycle it works. And the idea is here, of course, the great thing about chemical looping is that you can obtain the CO2 rather pure without any need for gas separation equipment or energy penalties. So how would this kind of system look? I showed the schematic. There are many ways to do this. Many designs have been proposed. The one that's perhaps most resolved in the literature is the coupled fluidized bed reactors. And here is one possibility, which is kind of related to what we're talking about in the Bio-Flex project. You have a high velocity air reactor, which is coupled to a cyclone, and then on the return side, the fuel reactor. So fluidized bed is a technology very well known for transferring particles like sand in conventional fluidized bed combustion. Here it's transferring oxygen carrier particles, but in the same size range as with normal in fluidized beds, perhaps 100 to 400 microns. And so the gas that is introduced to the air reactor is both the gas that is used to oxidize the particles, but it's also the gas that is used to transfer via drag forces the particles in the reactor system to the fuel reactor. In the fuel reactor, the fuel can be a gas, it can be a solid or a liquid, and it's usually fluidized with CO2, H2O, or recirculated gases. And what is very nice is that what we have seen in the community quite early is that type of similarity between chemical looping and a circulating fluidized bed. Here again on the right-hand side is the simple chemical looping concept, and on the left-hand side is a conventional circulating fluidized bed boiler with a riser, some external ducts, a particle lock, and then a return loop to the riser. So there are some similarities, and in principle you could see it as here. I think that the riser and the CFB would be the air reactor, and the particle lock would be the fuel reactor. So there are some very similarities. In fact, you can kind of see the CLC concept as a CFB with a small reactor unit on the return side. That is the fuel reactor. And what we're trying to leverage in this Bio-Flex project is this similarity. And I will get back to that. But to kind of summarize, why do we even bother about this? And basically, it's because, again, it's two reactor systems. You have a little bit more complicated system since you need to have functional materials that can provide the oxygen. So it's in many ways more complex than a normal CFB. But again, you need no or very little gas separation. And and you can have 100% CO2 capture, something that is not really amiable for other type of technologies, perhaps, or many other technologies. You can also see that this splitting of the fuel the fuel conversion, the fuel is only converted in the fuel reactor. So the air reactor should be rather clean. This means that you could perhaps see CLCs as a way to increase steam temperatures, because if you're using biomass, for instance, you would have corrosive gases which could harm the heat transfer surfaces. In many ways, you could think that this could be adjusted by the fact that you're decoupling the air from the fuel. And also the similarities again to our CFB means that you could likely combine the CLC process with a CFB process, something that could be a flexible system with lower technical and economic risks. So I kind of, again, at the Bio-Flex project, where we're trying to develop such a system,
I'm not sure if we lost.
Yes.
Yeah. Probably Tobias was lost.
He's frozen, right?
Yes.
Okay. So let's see if this comes back. So we wait a few seconds. Otherwise, I will ask Vincenzo to be prepared for the next presentation in case, and then we will take up from where we stopped. Vincenzo, in case you're ready. Vincenzo?
Yes, Fausto, I'm ready. Just I was just changing place.
Okay. So I think there is a problem with the connection from Chalmers because I don't see Matthias Tobias, sorry, in the list of participants. So I would suggest that we start with Vincenzo, and then if Tobias is able to join again, then we will continue. Vincenzo, please.
Okay.
This case is the coupled project, and while you are going to share, I will take the opportunity again to remind that this year there is the international conference on chemical looping. Oh yeah, I see Tobias arriving. Let's see if it works. Tobias.
Can you hear me?
Yes.
So I don't know what happened there really, but
Yes, we were out of the meeting for a while. It seems like.
Yes.
Did you hear us before?
Yes. Now we hear you, but before you were frozen and then left the meeting. Oh, kicked out of the meeting. I'm not sure.
Okay, I don't know why this was, but okay. So we will take back. I don't know where we were, but I will. Yeah, kan du ta tillbaka den?
Yes, we take back.
Yeah.
So please share again.
Du kan ta det till den där vi var innan.
Yes, you can continue, please.
Yeah, no. Okay. Yeah, so but I'm not quite sure where I was, but I will go on here. Basically what we're doing a bit and with atomistic modeling is to from DFT or density functional theory determining thermodynamic properties which we can use in multi-phase equilibrium calculations. And why do we want to do this? Well, you can do this for many reasons, for a better understanding of the thermodynamics. But where we have used it is basically to try to extend the different phase diagrams for oxygen carrier ash interactions. Biomass has a lot of reactive ash components, which could be very problematic, like alkali, chlorides, and things like this. And sometimes the thermodynamic data is not really there. So we use these type of methods in order to get a better understanding of the type of phases that you can get and where you can get these phases. We also use a very detailed characterization of oxygen carriers or oxygen carrier particles using different type of basically when you have a reactor and you have biomass and you have these different species, you can have an evolution of both the chemical and the physical nature on the particles. And we use tools such as XRD, SEMI-DX, XPS in order to probe both the bulk of the oxygen carrier particles, but also the surface of the oxygen particles. And this we do with impurities such as sulfur or nitrogen, but also trace metals like zinc, copper, or lead we have done, because and this has been related to, again, waste fuels, perhaps not biomass, but municipal solid waste or RDF can contain trace elements of and corrosive elements which are not very, very good. And the fact that you're in normal replacing kind of sand in a fluidized bed systems with oxygen carriers, you can have different type of chemical processes than you would have in a normal fluidized beds. And we also use, in order to test oxygen carriers, we use batch reactors and small batch reactors were a few centimeters in size, in order to look at basically more processes such as reactivity, defluidization, microstructure evolution, and things like this. Perhaps more interesting for the Bio-Flex project here at Chalmers, we are using, we also look at pilot operations, both in cold flow models and in pilot operations. And here we have a range of pilot units between a few watts to 100 kilowatts, and a range of cold flow models where we can look at fluidization phenomena. For one of the main units that we are using in the Bio-Flex project is a 10 kilowatt pilot unit, very similar to the unit that I showed in the beginning, if you remember. And this unit is currently being adapted for the Bio-Flex project, including the construction of a post-oxidation chamber. And currently we are also using some advanced methods in order to improve the fuel conversion in the fuel reactor. And what we're doing here is utilizing a concept called confined or packed fluidized beds. Basically what we're doing is that in the fuel reactor, when you really want to get good conversion of the fuel to CO2, which may be problematic due to the fact that the volatiles can disappear from the or not have good contact with the oxygen carriers. So what we're trying to do here is to use internal structures in order to break up and obtain a better mass transfer, better contact between the fuel or the fuel gases in the fuel reactor. And this is something that we here at Chalmers and at the CSIC are currently looking into, and which we will also operate at larger scale in the Darmstadt unit, which Jochen mentioned. So basically, that's kind of the levels that we're working on at Chalmers. And I would just like to say that I think that the one thing that is
I think we lost again.
Yeah.
Tobias, if you hear us, we lost you again. Probably is not connected. So in this case, we were very close to the end of the presentation. So I would suggest that Vincenzo takes over now. Vincenzo, you are there?
Yeah. To take the right presentation, just this one. And Can you see full screen?
Yes, we can. Please continue.
Oh, are you sure?
Yes,
See
please,
Tobias.
please continue, because I think in view of time, we should continue.
Okay, just wanted to check. Okay, because I see Tobias just joining. That's why I asked that. Okay, so what I'm going to do today, I'm going to present some technical knowledge about the project Coupled. So you've seen before the initial presentation what we are going to do in the project. Now, what I'm going to say today is that I'm going to present the idea of producing syngas by using chemical looping, what is the industrial implementation and the value chain, and I will go a little bit more in detail on the existing background in terms of chemical looping reforming using CO2 and chemical looping reverse water gas shift using, again, CO2 and in this case, green hydrogen. Now, you have seen before from Tobias' presentation, but also in a previous general presentation, that most of research is typically occurring in circulating fluidized bed. But there is also another way to carry out chemical looping, which is with packed bed. Now, looking at the two concepts, there are pros and cons. Obviously, oxygen carrier has been widely developed for fluidized bed. Plant operation being primarily continuous are much easier in fluidized bed than in packed bed. On the other hand, high pressure operation are not straightforward with fluidized bed, while are much easier with packed bed reactor. There is no gas solid separation to be implemented in a packed bed reactor. There is less solid handling, but on the other hand, there is more complexity, especially when we look at valves which are needed. This also reflects in the scale up. So you can see that in terms of technology readiness level, fluidized bed have been already been built and tested up to 3 megawatt scale. On the other hand, the replicability of the design is not that easy, while in case of packed bed reactor, this applies much easier. There is a supply chain for fluidized bed, which is in place, while for packed bed is still under development. In terms of industrial application, the use of fixed bed might allow to use on multiple sectors. As a fuel source, fluidized bed are much flexible, as you can use solid, liquid, and gas, while with packed bed reactor is primarily gas phase. And in terms of replicability of performance, this is something that is still ongoing in terms of understanding how lab scale translates into large scale. So that's a kind of a wider comparison between the two options. Now, as I said before, this project and the research activity in general I'm being carried out in the past 10 plus years. It's more related to packed bed reactor, and you can see here some example of what has been done in the past year. So we have some activity to carry out at the Eindhoven University of Technology for the Glamour project. We have done also now currently building a full-scale hydrogen plant for chemical looping in Manchester, and there has been a testing campaign for a single-scale reactor during the C4U project, which involve calcium and copper technology. So for the Coupled project, as I say, we are looking at packed bed reactor. So if we consider the combination of oxidation reduction and syngas generation, you can see that for the oxidation, we will generate nitrogen at high pressure by feeding air. Then we can carry out reduction by using waste of gas such as blast furnace, electric arc furnace gas, flare gas, or waste to energy gases. And from there, we will get a certain stream of CO2-rich stream, which will be later on purified. And finally, we do the syngas generation by combining either refinery gas, biogas, or green hydrogen together with CO2. Now, the syngas generated from that will be later on used for producing either iron, methanol, DME, liquid fuel, or can also be considered for biomethane. So we have a set of reaction, oxidation, which is highly exothermic and primarily used to generate high temperature solid in the bed. The reduction, which is in this case carried out with different gases and is primarily needed for reduce the material and make it ready as a catalyst. For the final step, which is the syngas generation, where endothermic reaction occur, so the syngas is generated. At the same time, the temperature of the bed drops down again, ready for the next oxidation. So whatever you're going to see here as a results, you can also find in previous work carried out at the University of Manchester in particular. So feel free to ask questions, but also you can go more in detail by consulting those publications which are here. So most of the testing, which is the background of the research carried out here, is being carried out with the system here in Manchester. So it's a reactor of 1 meter length and 35 millimeter internal diameter, where there are multiple thermocouple needed to measure the temperature inside the reactor. So for the chemical looping reforming, so again, the set of reaction is the same, and most of the testing here has been done by using both CO2 and steam. So we did in terms of oxidation, so we tested different airflow rate through the reactor by using 1, 3, and 5 bar and different temperatures at the inlet. And in general, we saw that there is a substantial temperature rise during the oxidation, which can go up to 300 to 400 degrees Celsius. Also, we did some comparative modeling and in 1D and 2D. And one of the important points that we find out by doing this, looking at the replicability, it's also that if you a proper modeling is not considered, we can underestimate substantially the temperature rise at the solid more than at the thermocouple. And this can be reason of safety, because our reactor, for instance, was designed to work at 1000 degrees Celsius, but we realized that 1000 degrees Celsius in the thermocouple was almost 1200 degrees Celsius in the reactor. So there is some serious safety that always have to be taken into account. In terms of reduction, we carry out several reduction testing at different temperature from 600 to 900 by using either hydrogen and CO, where we could see the fuel slip and the breakthrough testing. We did also something with methane, and we noticed, for instance, in case of nickel, that at the very beginning, there is always a certain nickel fuel slip, and this is because the nickel oxide is not really a good catalyst for is not really a good material for methane oxidation. But as soon as some of the nickel oxide becomes nickel, methane starts to break, so the reduction is carried out by hydrogen and CO rather than methane. And in general, again, we could be able to match reasonably well the breakthrough curves with modeling. And we found out that at higher temperature is where the model obviously works better, because the kinetics are also faster, I guess. We did some multiple cycles. So what you see here is a complete cycle of oxidation, reduction, and reforming. And what is quite interesting to notice here is that for the reduction and oxidation, we can see a very well-defined breakthrough. That's the case of the oxidation, and that's the case of the reduction. And just a moment, it's always a big slide. In case of reforming, the bed behaves as a catalytic reactor. So what is happening is that the temperature decrease and the heat removal of the bed occur, but at the same time, we form hydrogen and CO as a syngas. We did the same exact testing also using 5 bar instead of 1 bar. In both cases, we keep the temperature at 600 degrees Celsius in the furnace just to compensate the heat losses. And we were able to replicate this testing for 4 consecutive cycles. So it's a proof of concept which was quite substantially confirming the performance and the repeatability of the results. We did the same also with dry reforming. Again, in this case, we saw that the main difference is in the composition we generate during the reforming, which is higher in CO. But the good point is that we could control the final composition because it's substantially linked to the equilibrium. Another important point is that for the dry reforming that we did, it was easier also to control the experimental facility because no water was involved in this case. But an important point is that the temperature profiles that you see here are very well defined. And despite there are some heat losses, you can clearly see the impact of exothermic and endothermic reaction, even if we are in a laboratory scale facility. Again, in this case, we could do the validation by using by Korean multiple cycle and by testing up to 50 normal liter per minute gases of different composition. There is some sensitivity analysis also on the reforming, and what you can see here is that by changing temperature and changing pressure, still provide a close, predictable composition at the one that you can find at the equilibrium. We were also able to compare those results and seeing the case of steam reforming, dry reforming, but also steam and dry reforming together. And the reason we did that is because one of the things that we wanted to check was the hydrogen to CO ratio, which you can imagine is very important for the coupled project where we are going to produce syngas for Fischer Tropsch. Then moving to the reverse water gas shift. So what we did in this case was to try to operate a similar methodology, but just try to use a different gas for the syngas generation. Now, we did this testing with copper-based material. And again, in this case, as I said, the syngas generation is coming by feeding hydrogen, CO2, and getting hydrogen and CO. So the first trial we did was to replicate the breakthrough testing at 600 degrees Celsius. So you can see that for the oxidation and for the reduction, we had a very close overlap of the different cycle. And then we move on to the testing. Now, by having a sequence of oxidation, reduction, and reverse water gas shift, we could basically see that, first of all, we had an actual temperature profile consistent with the expected heat management. That means that heat was generating during the oxidation, It was slightly reduced during the reduction, primarily because of heat losses and a little bit of cooling at the beginning of the bed because of the heat front. And then during the reverse water gas shift, we start to see that the temperature drops quite substantially, becoming ready again for the next step. We could operate this for 5 consecutive cycles for over longer than 1 hour, so that were short cycle. So we could validate again the concept in this case. And another interesting things by looking at the thermocouple profile over the time is where you see that when there is a heat losses, you see the temperature drops, let's say, kind of constantly with a certain slope. But then as soon as we start to have the reverse water gas shift, you see that the slope change. So that means that the temperature drops faster. That's because of heat losses start to be also added to the heat of the reaction. So again, it's another evidence that experimentally speaking, the project, the concept sounds and it makes sense to remove heat by using chemical reaction. So in this case, again, the key point was to monitoring the hydrogen to CO ratio, and that's what we did by using different hydrogen to CO2 ratio and different temperature. And also we did the same check with the pressure. In terms of pressure, you can see that the difference is not that relevant. So you can see again, because of reverse water gas shift is a equimolar reaction, and because the system is not far from the equilibrium, you can see that there is not big difference between operating at different pressure. So that's what I was mentioning before about replicability, and that's what happens when you can replicate similar condition by using similar results by using different operating condition. We did also some study in terms of life cycle and process assessment. In this case, what we did is that together with a chemical looping, we combined an electrolyzer system and a Fischer-Tropsch reactor. And then we could recover from the system C7, C12, C16, while any other gas coming from light gases were used to add further syngas to the system. Now, the major things to say is that for this case, we could basically, so this is the, we could see that obviously the climate change performance becomes quite substantial, are still high if the electrolyzer are powered by grid. But if we use, as it was for the CCU2, electricity from wind, you see that we can almost half the existing climate change impact of steel industry, which was in this case the gas we used for the reduction. So it's not a way to reach net zero, but it's a way to drop by 50% CO2 emission from a steel plant, at the same time generate liquid fuel from recovered CO2. So let me move to the conclusion. I think I'm pretty much on time. So generally speaking, soundness of the technology. So the reason why we are looking at the scale up with COUPLED is because at TRL 4 and 5, we demonstrated that this chemical looping in packed bed reactor is feasible. Now, the goal at TRL 7, the goal in COUPLED is to reach TRL 7 and to use it in an integrated unit. In terms of operating condition, we saw that the technology can operate at different pressure. We could accumulate long-term operation, which is also the current goal at higher scale. While in Manchester, we are trying to do hydrogen production, so looking at very high pressure, which is 30 bar. For the COUPLED project, we are planning to stay close to 7 bar because it's also relevant for the feedstock that we are using. As far as material is concerned, so we have been testing, extensive testing has been done with nickel, copper, and iron oxide. This is also research done together with Johnson Matthey, who has been and is also involved in this project. Well, we could reach more than reach 100 hours with all this material, but the goal for the COUPLED project is to use 200 kilograms material bed and operate with copper or nickel-based material, depending if it's dry, if it's reforming or reverse water gas shift. Finally, the other point is the flexibility and modularity of the technology. This is a very important aspect because modular technology allows to have a scale up which is not which does not require an immediate build of a large scale plant, but it can be carried out step by step. So that's a way to de-risk financially and also technically the technology. And another point is that while chemical looping reforming has been historically used for hydrogen production, we see that there is also an avenue for CO2 utilization, and in particular, we believe the syngas generation is a very key point because it's a way also to detach chemical looping technology development with CO2 capture and storage technology, and it might provide still an industrial interest from industries who are interested in syngas generation for methanol or for other processes. So the technology has a less an environmental barrier lower than the case we saw before. I think that's all from my side. sorry if I be repetitive, but I want again to stress, well, I'm happy to answer any question, but I'm happy to remind to people who just joined that we have this year the 8th International Conference on Chemical Looping in Manchester, and the absolute submission deadline is approaching, and it's the 27th of February. And I really wish to see as many people as possible in Manchester to discuss new development on chemical looping. Thank you for your attention and happy to answer any question.
Thank you very much, Vincenzo, for the nice presentation. Of course, for the participants, if you have any question, you can ask in the chat. I have 2 questions myself because I don't see a question in the chat at the moment yet. The first one is the reduction. You have a reduction stage to prepare the catalyst, but it's also endothermic reaction, right? So my question is why you need that, especially when you do reverse water gas shift, because you have a mixture of CO2 and hydrogen. Can't you just put together reduction and reverse water gas shift together?
Yes. So for the reverse water gas shift, yes, it's you can do that. So as a matter of fact, one of the options is to have the system as a standalone reverse water gas shift plant, so you don't need the waste gases. On the other hand, when you use when you have biogas, as I was showing before, it's very important to make sure that if you use methane for the reduction, you will have this fuel slip at the beginning. So that's an energy loss, and this is also an energy cost that has to be considered. But it's true, reduction and reforming can occur at the same time. The only point is that from the outlet perspective, you will get two different gas composition. The first one is rich in CO2, which is a CO2 rich stream that will have to go for CO2 separation, purification, and whatever usage will be done later on, either storage or utilization, while the second part of the composition is a syngas, and that's what your important output of the process.
Thank you very much, Vincenzo. The other question is related to the catalyst or oxygen carrier, because you show very good results on the modeling, but you also show a picture where the oxygen carrier that you are using, the particles are very similar, perhaps just a little bit bigger than what a fluidized bed probably will use. But when you do the scale up, the particle should be much bigger, I guess.
Yeah, so correct. So the one here is in the order of, well, I mean, it's quite big, I would say, it's because you can see the particle are in the order of almost a few millimeters. We did test actually bigger particle and larger size in our reactor, in particular for the recycle project. I don't have results here to show. So
but okay, the question was
yes.
not, sorry if I interrupt also in view of time, the question was not that. The question is, when you do the bigger particle, do you need to introduce also a particle modeling inside your reactor modeling? Or
no, we haven't done it yet. You probably want to take into account the you want to maybe validate the kinetics, or you may need to revise the kinetics because you may have some additional mass transfer at the particle scale.
Mm-hmm.
But for modeling perspective, we did not add the particle model to the process, to the existing model.
Perhaps in coupled, you have to look at this as well, right? The particle will be bigger, I guess.
Yes, it is bigger.
Yeah. Okay. So thank you very much. I don't see anyone asking question in the chat. If that is the case, we wait for the end of this meeting. Thank you very much, Vincenzo, again. And now I would like to ask Jochen to give the presentation of Bio-MeGaFuel.
Okay, 1 second. Yes, welcome all to this presentation about Bio-MeGaFuel, in particular about the pilot testing of a chemical looping gasification for biofuel production. So just an overview what I will talk about. I will briefly explain the gasification process also in comparison with other possible gasification processes. Then, since we have done some pilot tests already in up to 1 megawatt scale, I will show a few results of previous tests, then some new results in the Bio-MeGaFuel projects, which are mainly in small scale, and then give an outlook on the planned pilot tests at 1 megawatt scale. Yeah, first, again, to the overall process concept. So in this presentation, I will talk mainly about the gasification project, and the main objective of gasification is to convert a low-value biogenic residue and waste into a nitrogen-free syngas, mainly consisting of water, of hydrogen and carbon monoxide. So here we need a nitrogen-free syngas because this would, if we have some nitrogen in the syngas, this would be ballast in the system. So inert material we have to separate and recycle. So this would decrease the efficiency, and the main, let's say, the adducts for the methanol synthesis are hydrogen and carbon monoxide. So any methane or other hydrocarbons, they cannot be converted in the system. So this is important to know because I will come back to this issue later. Yeah, first, before I go into the details, I will explain some of the existing gasification technology. So let's say the most proven conventional gasification technology is oxy gasification, which means that the feedstock reacts with a mixture of oxygen and water vapor to produce here also nitrogen-free syngas. There are several commercial technologies available, like the high temperature Winkler gasification, which is owned by Gidara, which is also a project partner in this project, in the Bio-MeGaFuel project, and this will also be used here as a reference for the chemical looping gasification. But there are also other technology based on circulating fluid aspect or even a drain flow gasification. Let's say the main drawback here of oxy gasification is that we need technically pure oxygen, which is usually produced in an air separation unit, and this requires energy, of course. So this is an energy penalty. And yeah, the main advantage, or one of the big advantages, is that we have a nitrogen-free syngas, and all the carbon which is fed into the fuel is then also contained in the syngas. So we can, in principle, then convert all the carbon into valuable products. Another possibility, which is already also commercially proven, is indirect gasification. So here, maybe just to come back to the oxy gasification, so we need this oxygen to a partial oxidation of the fuel to provide the heat for the gasification reaction. So gasification in general is endothermal. So we need some oxygen that is combusted to produce energy to gasify the rest of the material. And in indirect gasification, this energy is not converted in the gasifier itself, but it's converted in an external combustion chamber. And the heat is transported using an inert material. This can be sand or any other, usually it's olivine is used in such system to transport the heat into the gasifier. Then we can fluidize with only steam, and we can reach a syngas also with rather high hydrogen content. But we need some carbon in the combustor or any kind of fuel in the combustor to produce this heat. So usually the carbon, we have only let's say a partial gasification in the gasifier, and the remaining carbon is then burned in the combustor to provide the heat. If this is not enough for heat production, it's also possible to have an additional feed of fuel into the combustor. So the benefit is here that we do not need this pure oxygen, so no air separation needed. But we have one drawback, is that the carbon which is converted in the combustor generates CO2 at the exit of this combustor. So this carbon is not contained in the syngas and then can also be not used in downstream process. And the CO2 here also is emitted. So then if we want to avoid this emission of the CO2, then we have to do a separate CO2 capture here. And the chemical looping gasification, it combines, I would say, the two benefits of oxygasification, indirect gasification by using a metal oxide. So here the energy which is needed for the gasification is transported into the fuel reactor by a hot metal oxide. So there is a heat transfer from the air reactor to the fuel reactor, but it also transports oxygen here, which is also used for a partial oxidation in the fuel reactor. And then leaving the fuel reactor, we have the reduced metal oxide, which is then reoxidized in the air reactor, and this is a strongly exothermal reaction, and then generating the heat also for the gasification reaction. So we have also we don't need an air separation unit in this process, but also all the carbon is finally ends up in the fuel reactor, at least in an ideal case. It could, of course, be that we don't have a full gasification, and then parts of the carbon could also end up in the air reactor. But ideally, we can have all the carbon in the fuel reactor. Yeah. So here again, a scheme of the chemical looping gasification reaction. I already explained the main principle. So we have a metal oxide as an energy carrier here. So we have a temperature difference between air and fuel reactor, but also providing oxygen. And looking a bit more into the detail of the fuel reactor, so we are putting in biomass as a feed, and this biomass is heated up and de-volatilized, so producing volatiles like methane and other hydrocarbons, also water vapors, carbon monoxide, and also hydrogen, also volatile. And these volatiles, they then react at least partly react with the oxygen carrier to form some CO2 and water vapor. But the remaining biomass, which is a char, is then gasified with steam and CO2 to produce some additional syngas, CO, water, hydrogen, and this is also partially oxidized to CO2 and H2O. So we have a mixture of, in the end, a mixture of carbon monoxide, hydrogen, carbon dioxide, water vapor, and also some unconverted hydrocarbons at the exit. But let's say we have one main challenge with this inherently, I would say, in the process, is that it is desired to limit the oxygen transport from the air reactor to the fuel reactor. So if we have a high oxygen transport, we have the problem that too much of the syngas is converted to CO2. This is we don't want. We want as much as possible syngas at the exit of the fuel reactor, which means as much as hydrogen and carbon monoxide as possible. But we also need a high heat transfer from the air reactor to the fuel reactor because we have this endothermic gasification reaction. So we have to maintain the high heat transfer to sustain the endothermic reaction. And this is, of course, a conflict because if we maximize here the transfer of heat and oxygen carrier, then we also have a high conversion of syngas. And this is done. This challenge is faced by limiting the air input into the air reactor. So we have only, let's say, a partial or not full oxidation, only a partial oxidation of the metal oxide. And by this, we can maintain the high circulation between the reactor, but limit the transfer of oxygen. So if we typically, this reactor system operated as two circulating fluidized bed reactors. And here we have another challenge, I would say. So if we reduce the air here into the air reactor, then we are also reducing the overall velocity in the air reactor, which means less particles are entrained at the top of the reactor and can then be transferred to the fuel reactor. And in our pilot plant, I will show some results later on. We have faced this by recirculating some of the depleted air, or from consisting mainly of nitrogen, back to the bottom here to maintain a high velocity in the air reactor to enable a high transfer of solids. But this, of course, comes with some, let's say, energy penalty because we have to heat up this recycled gas again in the air reactor. Okay, now here an overview of the 1 megawatt chemical looping pilot plant. So on this photograph, you can see the facilities located in Darmstadt. This building here, this high building in the middle, it contains the chemical looping unit, the coupled fluidized bed reactor system. And then on the right-hand side, these towers, they are syngas cleaning plant. It contains various steps for syngas cleaning, and at the very end, an amine scrubbing system to remove the CO2. And these are these columns you can see here. And then we also have possibilities to test for synthesis, like Fischer-Tropsch or methanol synthesis in these containers you can see here. On the left-hand side, you can see a drawing, a CAD drawing of the chemical looping system. On the left-hand side, that's the air reactor with the cyclone. Then the particles fall down. We have the possibilities for internal circulation, but most of the particles are then transferred into the fuel reactor. They are then circulating here in the fuel reactor via cyclone back to the air reactor. For the testing so far, we have mainly used ilmenite. Ilmenite has been proven to be let's say, a good oxygen carrier for chemical looping combustion. And in the Clara project, which was funded also by the EU and ended a couple of years ago, It was also proven that ilmenite works very well for the gasification reaction. So ilmenite is an ore, contains titanium and iron, and comparatively cheap compared to, let's say, synthetic oxygen carriers. And if we use residues or wastes in the chemical looping process, it's important to have an oxygen carrier that is not too expensive, because there will be some kind of consumption of the oxygen carrier over time, a degradation of oxygen, mainly due to attrition. So we are producing some fines in the system, and they cannot be kept in the cycle and will then exit via the top of the cycle. In the Clara project, we have tested three kinds of biomass: and industrial wood pellets, then pellets made from pine forest residues, and also some pellets made from wheat straw. We had around 40 days of testing, 24/7 mode. So when we once heat up the plant, we operate for 1 or 2 weeks at the same time, and then shut down the plant. And this was in 2022. We achieved more than 400 hours of chemical looping gasification operation within this time period. And then in 2 later projects called Verena, it's a German-funded project, and Louise, an ACT project, for the first time, we tested some waste-derived fuels, SRF pellets, for around 7 days of testing. Unfortunately, we could not maintain a very long period of operation due to some challenges in the infrastructure of the system. So we have only uninterrupted operations. So we have some results, but maybe these are not so representative as the ones from the biomass, because here we could achieve a stable and also autothermal operation. Here are some results from the Clara project related to the cold gas efficiency. So the cold gas efficiency is more or less the energy contained in the syngas in terms of hydrogen, carbon monoxide, and also methane divided by the energy contained in the feedstock. Principle, we know from gasification that the higher the lambda is, so lambda is the stoichiometry of the overall system. So stoichiometry of 1 would mean that we have as much as oxygen as we need for the complete combustion. So when we increase the lambda, which means the oxygen in the system, then more and more syngas is converted to CO2, so the cold gas efficiency will decrease. And that's what we also saw in the chemical looping gasification system, when we decreased the effective lambda in the system. So does not only mean the oxygen which is added to the air reactor, but the oxygen which is finally also transferred to the fuel reactor. So we could, let's say, maximize the cold gas efficiency by decreasing this efficient lambda up to almost 50%. Now, maybe you remember that we aimed for 80%, but here we have to take into account that in the pilot plant, we have a lot of heat losses. We have heat losses through the surface walls, but we also have this problem I mentioned before, that we need some flue gas recirculation, and this is some additional heat loss. Okay, for the syngas yield, we can see in summary that we have let's say a good syngas yield, but we also have hydrocarbons like methane and also higher hydrocarbons like ethene here in a significant amount. And these hydrocarbons cannot be directly converted in a downstream methanol synthesis. One important issue is when we use this SRF, we have in general, we saw an increase of these hydrocarbons, so a significant increase. And although these are preliminary results, so this is one main, let's say, issue when we move from waste-derived fuels to from biomass fuels to waste-derived fuels, because here it contains a lot of plastics forming this kind of hydrocarbons. Now, looking specifically at the hydrocarbons, we could see that tars could be significantly reduced by increasing the temperature in the system. This is a well-known issue, I would say, that we need at least a certain temperature to crack the tars and remove the tars. And also here, if we compare here, as an example, light aromatics, BTX components, compare biomass with SRF, we can also see here an increase by a factor of 10 when we have this SRF. So this is a severe issue which needs to be handled when using SRF as a fuel. Now, in the Bio-MeGaFuel project, we are testing in various scales. So at CSIC, we have the 1.5 kilowatt scale, 20 kilowatt scale, and in Darmstadt, 1 megawatt scale, and we have 5 different. Maybe I can add that we will also test the HTW project owned by Chidara as a reference fuel, as a reference case. Then we have 5 different fuels: wastewood, olive pits. We have buckwheat pellets, spruce, and treetops branches, but also microalgae. And some of the fuels like wastewood will be also tested at a larger scale. We have not yet decided whether at 1 megawatt we will go for the olive pits or for the buckwheat pellets, because we expect some problems, I would say, with agglomeration, because agricultural residus usually have a low ash melting behavior, but therefore we need this small scale test to de-risk let's say the test in the 1 megawatt part, because here we have to convert quite large amounts, like 20 to 50 tons of this biomass. Now, looking at the analysis of these biomasses, they look rather similar at the first glance, but they have some distinct differences, like microalgae have a high ash content, for example. But let's say the main difference is not, let's say, the content itself, but it's the ash composition. So some of these have a rather high alkali content, like this residues, and also the microalgae. And as mentioned before, this can cause agglomeration and also corrosion in downstream process. So this has to be investigated in detail. That's why we have done some tests in a small scale. So these have been done at CSIC in Spain. As an example, with wastewood type B, some tests. So there have been some variations in the lambda here, let's say in the oxygen excess. So here at a very low lambda, high lambda, and intermediate lambda, and we can see the same as we have seen before. So a low lambda, then we have high hydrogen and CO. When we increase the lambda, this decreases quite a lot, and for the intermediate stage, it's more or less in between. And then also the fluidization has been changed from steam to CO2, and then we can see an increase in the CO2 concentration and also in the carbon monoxide concentration. Similar tests have also been done for the other types of feedstock, and so far let's say there have been no severe agglomerations being observed. So far we are quite confident that we can use at least the waste route and also make olive pits in the 1 megawatt plant. But this some tests are still pending here. Yeah, so for the planned tests in the 1 megawatt plant, as mentioned before, ilmenite will be the oxygen carrier. Also here, we will use the waste wood because we assume this is the most easy fuel because it's quite similar to conventional biomass like the pine forest residues we have tested before. So we expect that we have a smooth operation here. But then for the olive pits and the buckwheat, we are still waiting for some tests at a smaller scale to evaluate which is the most advantage fuels with the least, let's say, challenge related to agglomeration. So the idea is to do a test campaign of 14 days, 2 weeks this year to achieve at least 200 hours of chemical looping operation. And at the same time, we will also operate the gas cleaning unit to get really pure syngas containing only hydrogen, carbon monoxide and carbon monoxide and some remaining hydrocarbons. Okay, so this was a brief overview of the tests that have been done in Bio-MeGaFuel. And I would like to thank the European Union for the funding this project and also thank you for your attention.
Thank you very much for the nice presentation. I don't see yet questions for you in the chat. I have a question myself about the byproducts of, especially when you use different type of biomass inside the gasifier. Do you expect different type of sulfur compound in the gas leaving the gasifier? And can you say something on concentrations?
Yes, there are of course different sulfur concentrations in the feedstock, especially in waste derived feedstock. There is an increased amount of sulfur. Maybe it can reach up to something around 1000 ppm of hydrogen sulfide. But this can be removed in this downstream amine scrubbing system to a large degree. And yes, of course, amine scrubbing is known not to have 100%, I would say, removal. There will be some ppm left, but this can be finally cleaned by, for example, zinc oxide, garbage, or some active carbon or whatever. So this has been proven to work quite well.
So you don't expect any problem for the methanol reactor later when you do the integration?
No, this should not be a problem.
Okay, thank you very much. We have still some time for the roundtable. First, I would like to tell all the participants that we are making a video, so we will share the video of the webinar. And of course, we will ask also the presenter to send us the last version of the presentation. We will put also on the websites. So that should be possible for all of you to see the presentation again. And now I have a question before that, I see that there was a question for Vincenzo on the value chain, I think. Vincenzo, you want to answer this question for all the participants?
Yeah. I mean, I dropped the answer on the chat just in case people wants to see also the more detail. So the question was about availability of and the supply chain for packed bed reactors. So the reason why I think this is more complex at the moment is because the system is a new system. It operates under switching time, which is quite short. So valves, material for reactor pipings, they need to be designed to withstand this chemical and thermal stress. The temperature normally during the oxidation rise by 400 degrees Celsius, and then it drops and rise again. So these are challenges which need to be addressed. However, one of the things that is probably worth to mention is that there are similar technology which has been developed, licensed, and already industrially operated by several years. So one example from which we normally start with to identify similar solution is the technology called CATOFIN or CATADIEN, which are dehydrogenation process, which operate at low pressure in this case. But as I say, it's one way to start for similar technology.
But in that case, the temperature is a little bit lower, right?
It's around 650. It's lower temperature, but it's also different composition, which is another important point. There is no CO involved, for instance.
Okay, so still some thing to do. So you will look at this value chain also in coupled, or you live for a bigger scale?
No, we do. I mean, we have a project partner which is called EMI Remosa, and they are specialized in valves manufacturing. So they will, and they have been involved in the past on CATOFIN solutions. So they will support the research on that.
Yeah.
So to address one of these problems.
Okay, thank you very much. Then I have a question for all the participants, and I would like to start from one of the slides of Tobias. Unfortunately, there were some problems with the presentation, but I recall that clearly Tobias said we have failed because we speak about CO2 capture for a long time. Now, if you look at the chemical looping part, can you perhaps say where we failed? And what we should do more to bring this technology to the market?
Is the question for me?
For all of you, but I would start from you because I recall you said we failed, and I agree with you.
Well, maybe it's not. Maybe it's a whole value chain of organizations and people who have failed in some way. But I think that in general, the reason is, of course, that there have been very little incentives for both CCS from fossil fuels and no incentives at all for biomass. And I mean, these are costly. Even chemical looping is costly. So nobody will want to take that kind of. No stakeholders will take that type of risk in that type of environment. That's my view.
Yeah. The others. Yeah. The others have any comment?
Yeah. I fully agree with Tobias. So it's more or less the boundary conditions. So let's say we already demonstrated chemical looping a decade ago. I would say at the 1 megawatt scale, it was ready for scale up, but there was no one taking, let's say, the risk, the money to scale up, invest money in a scaled up unit. So recently we have this Cheers plan, which is a big step towards commercialization. But this step could have been done already 10 years ago. But at that time, no money and no real pressure was there for the utilities to invest in such technology.
Vincenzo, do you have any comment on that?
Just, yeah, I have a quick comment just to say that the main issue on moving towards commercial application is primarily because of CO2 capture. Is a problem not well regulated from policy perspective. So there is no incentives for technology uptaker to move on this. We see in the UK where they are slowly but trying to build a CCS cluster in different region, and we saw already many industry just not just back up their initial interest because they don't see at the moment a proper convenience. I guess the implementation at scale of net zero is something that is costly, and society has to be aware about that, that there will be a price for that. In Europe, it's particularly costing, which I understand why probably cheers would be possible in China, not maybe in Europe, and maybe a next step of chemical looping will a larger plant will be built still in China of that size. But on the other hand, I've seen in the past 10, 15 years on chemical looping a lot of interest on other solution where gas oil reaction can meet industry needs. The example I said before of dehydrogenation, as an example, is a chemical looping process as well. So it's something where you can see things happening. It's just that we need to probably involve the industry at the very beginning of the research to select together the same challenge and the same objectives. So that's my feeling on that.
Yeah, thank you very much. I have another question about the scale up, especially if we look at the Bio-FlexCLC and Bio-MeGaFuel. We try to use residues or biomass, and this is not big scale per se, right? So how far we are for the scale where we can use biomass? Because I don't think we need so many megawatts, right?
Yeah, I would say it's always a compromise between transporting big amounts of biomass to a centralized unit and then pay for the transport and have a very efficient and let's say using the economy of scale of a big plant, or have then decentralized units. But now when we add, I think it's for a conventional system, I think it's convenient to have these decentralized units for producing heat and power. But if we at the same time capture the CO2, it adds an additional problem that we also have to transport the CO2 from this side to centralized units. So maybe I would say if we have a CO2 capture unit, or maybe it makes sense to make this bigger as a conventional decentralized system. But yeah, it depends a lot on, I would say, on the availability of the CO2 infrastructure.
Yeah. Vincenzo, do you have any comment on this?
I mean, obviously, the scale for a packet reactor, it's something. I mean, it's one of the points where we are pushing a lot is the modularity concept. So the idea, probably at commercial scale, is to maybe define a small module, which might be the order of few megawatt of lower heating value, let's call it like this, and either applied in industries where the production is something limited to this amount, or having multiple of this unit when you're going to go to large scale. One of the points that I tried to stress before is that even for a large company who wants to develop this technology at large scale, the fact that you can implement this step by step, so in a time scale of 10 years, it's one way to avoid that you need to build a large plant and then suddenly you figured out that it's not convenient anymore because of problem which comes. So this is one of the advantages where modular technology can be a good solution still in a market like Europe or where we are going more to different sectors. So I guess the scale is it's critical to define a first of a kind market solution, but the advantage that it doesn't have to be very big. It can be small and it can be even for niche application, although it will not solve climate change.
Thank you very much. I want to take the time to thank again the speakers, Vincenzo, Tobias, Jochen, very much appreciated. As I said, this is one of the first webinars because both projects, or actually the three projects are one started and one and the other two in the middle. So I guess later this year and also next year we will have more results to show. I want to remind again what Vincenzo said. There is the chemical looping conference chaired by Vincenzo, so I guess he has some interest to invite all of you. But I hope that we see each other in person in Manchester. And of course, we also organized the winter school on gasification and membrane reactors, which is in February. So for students that want to participate or researchers that want to participate, you can check the website of OneCube and also on Eventbrite. With this, I want to thank you all again, also the participants. The video will be ready, I guess, end of this week. We will put on the social, and the presentation will be in the websites of Bio-MeGaFuel, in the Bio-FlexCLC, and in the COUPLED project that is almost ready, as I understood. Good. Thank you very much then, and see you for the next event.